Module 5 Investigation 3 Transformations of Polynomial Functions. You may recall transformations from high school. It's when the graph shifts. Like if you do a vertical transformation, the graph shifts up maybe k units, however many units, or down so many units. You could have a horizontal shift, horizontal translation. We could have reflections across the x or y axis. Number 1, the function g represents the height of a ball above the ground measured in feet. Where's my function g? Up here it is. I have my output here and my input here. In terms of the amount of time t measured in seconds, since the ball was thrown upward from the roof of a building, so I see that my initial time, when the time is 0, my initial height is 145, so my building must be 145 feet tall, and the ball is thrown upward, so I'm guessing that it looks something like this. Have some person here, they're on top of a building, they take a blue ball and they throw it upward, so I'm thinking they're throwing it straight up, goes up, and then it starts to come down, and based on the graph you can see that this point is the highest point, and then it comes down all the way to the ground because the height is 0. So the ground level is where the height is 0, and this up here where he throws the ball, the height is 145. So I don't want you guys to get confused and think that he was throwing it off the building, because it says it's just thrown upward, vertically upward. Let's see. Complete the table below by determining the average rate of change of the height of the ball above the ground measured in feet with respect to the amount of time t in seconds since the ball was thrown. Okay, the average rate of change for each of these intervals will simply be the change in height divided by the change in time, and that's final height minus initial height over final time minus initial time. So for this first one here, g of t represents the height, so it's 165 minus 145 over 0.5 minus 0. So that's 20 over a half, which is 40. Now I will quickly fill out the rest of the table. Okay, on to part B. What pattern do you notice in how the average rates of change of the height of the ball with respect to the number of seconds since the ball was thrown changes when considering 0.5 second increments of time? Let's see. So all of these are 0.5 increments of time. And what I notice is that the average rate of change is decreasing. We decrease by 16 here, then we decrease by 16 here, then by 16 here, then by 16 here, then by 16 here. So we notice that the average rates of change of the height of the ball with respect to the number of seconds since the ball was thrown decreases by 16 feet per each 0.5 second increment. So that tells us that the graph is concave down. You can see here that the graph is concave down. And again, we know that because the average rates of change are decreasing. We have a positive slope for any tangent line we draw here, a 0 slope at the top, then negative slopes down here, and the negative slopes getting more and more negative. Okay, let's see, what else can we draw from that? Anything else? To me, it's interesting that the difference of each of these is 16. This is a quadratic function. That's always going to happen with quadratic functions. If you look at the the rates of change, like the function that defines the rates of change, will be linear. Like you could say that we have a slope of -16 here. Anyways, moving on to part C. What does the point 2.5, 165 represent in the context of this situation? 2.5, 165, that represents, let's see, 2.5 seconds after the ball was thrown. The height above the ground in feet was 165. I think, is that right? Yep. That makes sense. He's still a little bit higher than he was when he started, so the ball is somewhere up here. We went up, we came back down, and the ball's somewhere around here. Okay. Number 2, a second ball is thrown from a platform that is exactly 5 feet above the point where the ball modeled by function g is thrown. Okay, let h be the function that models the distance-time relationship of this second ball. Assume the second ball follows the same trajectory as the first ball. Let's see. So a second ball is thrown from a platform 5 feet above where the first one was thrown. So if I go back to this picture here, it's like we have another person on a different building, and they have a ball, but I drew that totally wrong because they're actually 5 feet higher. So really they start like right here. They're just on some platform. Don't know where that platform leads to, but they have a ball and they throw it up. It says that it follows the same trajectory, so the same general sort of pattern. We go up, and just the difference is this one's going to go 5 feet higher than the other one. What do we want to do here? Let h be the function that models the distance-time relationship of this second ball. Complete the table at the right. So essentially just our function h, we're going to start 5 feet higher, so we're going to start at 150, and at any given period of time this second ball would be exactly 5 feet higher than the other one. It's kind of hard to draw this. Should just be more careful. I tried to draw it so that the change in height, this distance here between the black and the green, if we just the vertical distance, is always 5. So that would be function h. I'm not sure if I need that in my graph. I'm going to go ahead and take it off if possible. Okay. But anyway, all these heights are just 5 feet more than the heights for g. So that first one at 0 we're at 145. So this one will be 150. And let's see, the second one is 165. This one will be at 170. And I'm just going to go ahead and fill out the table. Just add 5 to each of these here. Okay, so we got our table there. The next question says, what does it mean for two balls to follow the same trajectory? For me, it meant that they followed generally the same sort of pattern in their behavior. The answer key says this: the distance-time relationship of the two balls is the same. When I drew H over here, probably don't know if I should have erased that. It had the exact same shape, it was just shifted up a little bit. So the relationship between those is pretty similar, just a vertical shift. Let's see, part C. How do the output values of function h compare with the output values of function g on the domain of h? Let's see, well, the output values of function h are 5 more than the output values of the function g for corresponding inputs. Sketch the function h on the same axis that g is sketched above. Okay, well, I already did that. Guess I'll do it again. Maybe a little bit more precisely with these coordinates. I just decided to draw the same rough sketch again. So this is h. This green one is just a vertical shift of g. Every point should be up 5 units. Let's see. Oh, I forgot to do part A. Complete the table at the right. Almost finished with that one. So the average rate of change in height over change in time, 20 over 0.5. 20 over half, that's 40 again. See, 182 minus 170 over a half, that's 12 over a half, which is 24. 182 minus, or 186 minus 182 is 4, divided by the half is 8. This is negative 4 divided by half is negative 8. Negative 12 divided by half is negative 24. 150 minus 170 is negative 20, divided by half is negative 40. What do we notice? The average rates of change are the same for these graphs. That makes sense. All we've done is shift the graph up, but the average rates of change, that relationship still holds. How do they compare? Well, they are the same. Express the function h in terms of g. Well, we know that h is just g of t plus 5. Just add 5 onto each output value. Let f be the function that describes the distance-time relationship of a ball whose distance above the ground is always 3 times as large as the initial ball's distance above the ground. Modeled by function g. Complete the table at the right. So, we're always 3 times as large here. That means we're going to start at 145 times 3. This is going to be a pretty big building, way up high, and we can't even see that on the graph here because the initial height will be 145 times 3. At 435. So that'll be pretty high. Let's go ahead and fill in the table. Already said this one would be 435. Then to get the next one, 165 times 3, 495. Just multiply each of these by 3. Okay, these are probably right. Now we can calculate the average rate of change. 495 minus 435 is 60, divided by half is 120. Going to do the same for the rest of these values. See an interesting pattern here. 120 is 40 times 3, 72. Let's see. That's 24 times 3. Then 24 is 8 times 3. Notice that all these rates of change values are just multiplied by 3 to get these over here. So I'm sure that that's going to be one of these questions. Part B, how do the output values of the function f compare with those of the function g? The output values of f are 3 times the output values of function g for corresponding inputs. How do the average rates of change of functions f and g compare on successive 1/2 second intervals? Well, the average rate of change of f is 3 times the average rate of change for g on successive 1/2 second intervals. Express the function f in terms of g. Well, f of t is 3 times g of t. We could just write 3g of t and understand that means multiplication. Okay, so that's an interesting finding, but it's not very surprising because here we're looking at the change in f over the change in time, and if each f value is 3 times as large as a value of g, then it makes sense. Let's see, I'm just going to write it out. Like if we do f final minus f initial over the change in time, those values of f are just 3 times the corresponding values of g. So that's 3. We factor out the 3. 3 times delta g over delta t. Number 4, let k be the function that models the distance-time relationship of a ball whose distance above the ground is always 3 times as large as the initial ball's distance above the ground. This ball was also thrown from a platform 5 feet higher than the ball modeled by function g. Over the summer, when I was first introduced to these pathways materials, the author of the textbook, Marilyn Carlson, came to MTSU and we worked on this problem, and I spent about 30 minutes saying that it was impossible. It just didn't make sense. How could you throw a ball from a platform 5 feet higher than that modeled by g and still have the distance be 3 times as large? It's impossible. If let's see, if the ball is thrown here 5 feet higher, then at that initial time, this ball is not 3 times as high as this one. How can the ball be way up here 3 times the initial height of this one and also be down here? It can't. So the question is worded kind of weird. Everybody else understood what it was asking, except me. But let's see, how should I put this? They're sort of saying, well, you go 5 feet higher and then you go 3 times that. So we're not really starting our ball here. We're gonna find some place like way up here. So it's, you go up 5 feet and then from this guy's perspective you go up 3 times. Kind of weird. So I'm just going to fill in this table with the interpretation that the author and my peers had. If you feel the same way I do about this problem, don't worry about it. I don't think I'm going to ask you guys to do this on the test just because I think it's weird. But let's go ahead and try to fill out this table. So we go up 5 feet. Where's function g? We go up 5 feet to 150, and then we multiply that by 3 to get 450. Easiest thing to do is just look at h, because we've already gone up 5, so we just multiply each of these by 3. 150 times 3 is 450. 170 times 3 is 510. Hold on a second. Never mind, that's not right. This question still doesn't make any sense to me. They're taking 145 and multiplying it by 3 and then adding 5 to it to get 440. So am I just the only one on the planet that doesn't understand how this makes sense? So to get the next one, 3 times as large as the initial ball's distance, and then 5 feet more. So 165 times 3 plus 5 is 500. Okay, I'm going to fill in this. The average rates of change, the change in output over the change in input. So 60 over a half is 120. And I'll go ahead and fill this. Let's see, does that one match anything else we've done so far? Matches the previous one where we were multiplying 3 times g of t. So how do the output values of the function k compare with function g? Well, we multiply them by 3 and then we add 5. How do the average rates of change of functions k and g compare on successive 1/2 second intervals of the domain k? They are 3 times larger. I should say that the average rate of change for k is 3 times as large as that for g on successive 1/2 second intervals. Express the function k in terms of g. K of t is 3 times g of t plus 5. But that really doesn't make sense how that is a function whose distance above the ground is always 3 times as large and the ball was thrown from a platform 5 feet higher than the ball modeled by function g. That doesn't make sense to me. Okay. Moving on. Let P be the function that is the reflection of the function g across the horizontal axis. Complete the table at right. So if we go back and take g and we reflect it across the horizontal axis. Let's see, that would mean that we have something like this. Oops. That's not perfect, but like this point here at 145, it'll be down here at negative 145. this maximum point here, which appears to be at 1.5, about 181, will be down here at negative 181. And then like this point here, well, it's on the x-axis, but this one looks like it's about, let's see, 50 right here, and so this point should be at about negative 50, if we drew that right. So you may note that all the values from G are just going to be negative. Negative 145, negative 165, negative 77, negative 181. We're just reflecting it over the horizontal axis, so they all become negative. And if we compute the average rate of change, negative 65 minus 145 is negative 20. Divide that by half, get negative 40. All of these values are just going to be the opposites of what we found for G. And so let's think about what's going on there. Here we always had, let's see, concave down, meaning our rate of change was decreasing, but now if this was our function, we'd start with a negative slope, get a zero slope, and then our slope would start to increase. We'd have an increasing rate of change. Does the function p make sense as a model of the time-distance relationship of a ball that is thrown from the ground? I would say no, because we can't have a ball going underground. We can't have negative values for height above the ground here. How do the output values of the function p compare with those of function g? They are all opposites, just the negatives. How do the average rates of change of functions p and g compare on successive 1/2 intervals of the domain? They are also opposites. I'm not spelling very good today. This has been a weird video lecture. Thanks for bearing with me. Express the function p in terms of g of p of t is just negative of g of t. Explain what the function w, defined by w of x equals 2g of x plus 7, represents in the context of the time relationship of the ball. I just put the book's answer here because this question again makes no sense to me. I don't think it's possible, but there's the answer.